This presentation examines the two-sample t-test for means, this time using artificial data together with MINITAB. So here is our test statistic and our alternate statistic, mu1 equals mu2 versus mu1 does not equal mu2. So we recognize right off the bat that this is a two-tailed test. Here are our statistics. Recognize both ends are large, so we satisfy the conditions of the central limit theorem. We also have to make sure that these are simple random samples, and of course these must be independent samples for us to be able to continue. Now our goal is going to be to construct data sets that have these characteristics. So I need to start with 65 items for my first data set. So I'm going to say random 65C1. That will generate 65 numbers from a Z population. Well, just because mu is 0 and sigma is 1 does not mean x bar will be 0 and s will be 1. But we'll take this data and we will convert it so x bar is indeed exactly 0 and s is exactly 1. That command is the center command. We say center C1, C1. So now we have x bar, mean of 0, standard deviation of 1. We want the standard deviation to be 9.3. So we're going to multiply everything in this data set by 9.3. And then we're going to add 52.1 to get the mean that we want. So let C1 equal 9.3 times C1 plus 52.1. And then we'll take a look at our descriptive statistics, and you will see that I have an N of 65 with a mean of exactly 52.1 and a standard deviation of 9.3. So we have the characteristics we need. Now we also have to generate an artificial data set for C2, so I need 72 items there. So the command is going to be random 72 into C2. And again, center C2, C2. So now the mean is exactly 0, the standard deviation is exactly 1. When I multiply by 12.5, the standard deviation will be 12.5 and the mean will still be 0. Then when I add 55.2, that will not change the standard deviation, but will change the mean. So the command there is going to be let C2 equal 12.5 times C2 plus 55.2. And now we can look at our descriptive statistics, and we have what we need there as well. So we have constructed two artificial data sets, C1 and C2, that will have the required characteristics. The command we use on MINITAB to do a two-sample t-test is two-sample. So we're going to say two-sample C1, C2. If there is no subcommand, it assumes it's a two-tailed test. If you have a one-tailed test, you must put in a subcommand, and we'll discuss that later. But this is a two-tailed test, so no subcommand is needed. And here's the results that we get. Notice it says t-test of difference equals 0. So again, mu1 minus mu2 equals 0, or mu1 equals mu2, versus not equal. So again, this tells us it's a two-tailed test here. Now it's giving us the test statistic, negative 1.66, the p-value of 0.100, and the degrees of freedom here, which is 130, very large degrees of freedom. So we have to determine is negative 1.66 an extreme p-value or not. Extreme t-value, well, the p-value tells us it's 0.1. So the likelihood of getting numbers this different from each other just by random chance is almost 10%, which is relatively high. So this is not an extreme t-value, not enough for us to throw out h0. So indeed, there's our null and alternate hypothesis, there is our test statistic t, and there is our relatively high p-value of 0.10. And we say since the p-value is large, we fail to reject h0, and there is not enough evidence to conclude that the two samples come from populations with different means. The population means may have been the same. We cannot be sure. Assuming this is true, the likelihood of getting samples this far apart is 10%. And since that's relatively large, we tell ourselves we cannot throw this out. We have to retain it as possible. Okay, now here will be a one-tailed test. We have h0 mu1 equals mu2 versus ha mu1 is less than mu2. And we have our statistics there. Again, notice both are greater than 30, so we don't need to concern ourselves with normality. We're going to create the artificial data sets. What will they look like? Random 44C1 puts 44 numbers into C1. Center C1, C1 makes them have a mean of exactly 0 and a standard deviation of exactly 1. Let C1 equal 4.3 times C1 plus 21.5. Converts it so the mean is exactly 21.5 and the standard deviation is exactly 4.3. For the second data set, random 56C2, putting 56 numbers chosen randomly from a Z. Center C2, C2 will make x bar exactly 0 and s exactly 1. And then to get the standard deviation we need 9.5, multiply that by C2, add the mean we need 25.2. This will generate two sets of data with the required characteristics. So take a look at a modified version of the describe command and you can see the count, the mean, the standard deviation for both C1 and C2 have the requirements that we need. So the command again is to sample C1, C2, but this time we want mu1 to be less than mu2. As we see, this is a one-tail test to the left. If it's a one-tail test to the left, the alternative hypothesis is -1. So we say to sample C1, C2, alternative -1 period, since HA is less than -1. And here's the first part of the results. Again, it gives us our descriptive statistics. And then notice it says here, since it's alternative -1, that corresponds to test of difference equals 0, mu1 minus mu2 equals 0, versus mu1 minus mu2 is less than 0, or mu1 is less than mu2. And then you can see we have our test statistic t, -2.60, our p-value of 0.006, very small p-value, and our degrees of freedom of 80. So a very small p-value tells us if we assume the null hypothesis is true, the chances of getting numbers like this just by random chance is 0.006. And since that's small, we say maybe it wasn't random chance. Maybe we should throw out the null hypothesis. So again, our null hypothesis, alternate hypothesis, test statistic, and p-value. Since the p-value is small, we reject H0. And this time we're going to say we have sufficient evidence to conclude that the first sample comes from a population with a smaller mean than does the second. So let's take a look at one more example. So this time we'll do a one-tailed test to the right. So we have our descriptive statistics, and again, both are larger than 30. We need to construct our artificial data sets. I need 62 numbers, random 62, C1, center C1, C1 to make them have a mean of exactly 0 and a standard deviation of exactly 1. Let C1 equal 12.5, the standard deviation, times C1 plus 58.6, the mean. That'll make C1 have a mean of exactly 58.6 and a standard deviation of exactly 12.5. Similarly, random 56 C2, center C2, C2, make it so that the x bar is exactly 0 and s is exactly 1. Multiply by 11.4 will convert the standard deviation to be 11.4. Add 56.5 will convert the mean to be exactly 56.5. And then we can look at the numbers, and indeed they match with what we expect them to be. So the command we need here is to sample C1, C2, but this time it's alternative 1. Why is that? Our HA is mu1 is greater than mu2. If mu1 is greater than mu2, our alternative hypothesis is positive 1. So alternative positive 1, period, is what we need here. And then you'll see the results. Notice I've highlighted alternative 1, and that tells me test of difference equals 0 versus greater than. Mu1 minus mu2 equals 0 versus mu1 minus mu2 is greater than 0. So alternative 1 corresponds to an alternative hypothesis of greater than. T-value of 0.95, that doesn't sound like a very extreme test statistic for T. P-value of 0.171, that tells us it's not extreme. And a degrees of freedom of 115, quite a large number of degrees of freedom. So assuming H0 is true, the probability of getting samples like this just by random chance, like this or worse in a sense, is 0.171, which is fairly high, which means it's reasonable for us to think that H0 may have been true. We can't be sure. So what is our conclusion? Again, mu1 equals mu2 versus mu1 is greater than mu2. Test statistic T, p-value is 0.171. We say since the p-value is large, we fail to reject H0, and there is not enough information to conclude that the first sample comes from a population with a larger mean. The population means may have been the same. We cannot be sure. So we have to hold on to H0 as probable or likely or possible, but we cannot throw it out because there's not enough evidence for us to say that it's not true. And that will conclude this presentation.